Good afternoon, you wonderful students. Hey, this is Dr. Mandis coming to you to talk to you about phase diagrams and heating curves. Last time I made a video about IMS and phase change. It's about where the next progression is to, hey, how about we just talk about phases and how they relate to one another and their temperatures, et cetera, et cetera. We're just going to start with phase diagrams. Phase diagrams you can just memorize, but it's good to understand them. And the whole gig about phase diagrams is basically it's a pressure versus temperature diagram. So picture you were in class and your teacher gave you a bunch of little data points, data point, data point, data point, data point, data point, data, a bunch of pressures and temperatures that you then wanted to plot. And so you're going to go over here on your graph and you go in and make a whole bunch of data points and you make a plot. You always did since you were like in fifth grade or whenever. But here's the gig. When you plot it, if the substance is a solid phase, make your data points red. The substances in the liquid phase, you want to make those data points green. And if the substances are going to be in a gas phase, well, we're going to make those data points blue. Like for instance, our gas data points, we're going to find out that every time you plot them, they're kind of down here at the bottom. Kind of makes sense. Low temperature, low pressure, high temperatures, that sort of gig. But anyway, let's not talk about that. At solids, we're going to find out that, hey, you're going to have a little thing that looks a lot like data points up here. I know it's a lot of data points. Just be patient. I'm getting somewhere with this. And for the liquids, we said they were going to be green. And the liquids are going to be, stuck down in here somewhere to a bunch up in here. And you say, hey, well, that's a freaking mess, man. Well, let's draw some boundaries in. There's some points where you have solids and liquids interacting, and there's a boundary here. Looks like there's some sort of boundary there, and another boundary there. So you get a diagram that kind of looks like that. You say, hey, I'm onto something. It looks like at areas of high pressure and low temperature, I'm a solid. That makes sense. Areas at high temperature and low pressure, gas. High temperature but add some pressure, that gas condenses and we move into what we call a liquid phase. That sort of makes sense. Cool, I get this. All right. At the boundary lines, these guys, you're on the boundary between two states. When you're the boundary between two states, you got 1 foot in one state, 1 foot in the other. You're in both states, man. Same thing here. The boundary lines represent both phases. That's a key thing. Both phases coexisting means you're at a phase change. Say it again. Both phases coexisting indicates that you definitely are at a phase change. So let's go to a prettier version of the diagram. If I could scroll to this diagram, okay? And I have wrote up what I sort of give out in my notes here. Here you go. There your boundary lines are right there. And so you see that, hey, those are the phase change lines. So that if I do from pressure, it's any pressure over to, say, this line between solids and liquids, that means a melting. The temperature that corresponds to that must be the temperature which melting occurs. So that's a melting point. If I continue onward, say, hey, liquid, I'm off scale here, but the temperature corresponds to that liquid gas interchange. That'd be a boiling point. So that makes sense. There are lots of melting points, lots of boiling points. That will just depend upon what the pressure is. Well, normally we just live under 1 atmosphere of pressure. As a chemist, you can change pressure, but normally there's 1 atmosphere of pressure. 1 atmosphere of pressure takes you to what we call a normal boiling point, melting point in this case. Just gets you down here to a normal melting point. The melting is occurring here on the boundary line. The melting point is at the temperature. If we continue our little discussion and go all the way out here, this would be the normal boiling, and the normal boiling point is the temperature which the normal boiling occurs. Cool beans? That makes a lot of sense. But there are two special little points I should bring out. One is here, all 3 phases at that one little interjunction of those 3 lines. That is the triple point. Triple point is where all the phases coexist. It's just some trivia. Out here, we got a critical point. Okay, critical point is a unique spot. Out here for the critical point up here, like if we continued our curve outwards, we had solid, we got liquids, we have gases, but out here is where the sidewalk ends. You have a supercritical fluid. They have properties of both gases and liquids. It's a unique situation. Not really germane to general chemistry, but if you study onwards, you can find out more. So let's get into this whole idea of just phase change and talk about heating something. And all I want to do is ask you, say, look, man, you got a pot of water. Okay, we got water in a pot and we're going to heat it. At what temperature will that water boil? And you would say 100 degrees C, I hope. Maybe you're stuck in Fahrenheit and you say 212. Whatever. If the water's boiling, you got it on your stove, the burner is red freaking hot, and it's boiling away, you know it's absorbing heat from that red hot burner. So if you had to graph the temperature of that water while it was boiling, you'd probably think the temperature would go up because it's absorbing heat. Well, it doesn't go up. If you remember about IMFs, at a phase change, the IMF goes into the added heat energy is going into breaking the IMF. Okay, overcoming that IMF to create the new motion. As we're boiling, the gases have to translate across space. We got to break the IMF and do it. So at phase changes, temperatures are constant. That's why the boiling point of water is always 100. Okay, at normal atmospheres. If you're going to graph it from the solid to the gas, the solid would heat up, eventually start to melt. It would stay flat while it's melting. Then it would heat up again when it's done melting. Eventually it starts to boil, stays flat while it's boiling. Then it heats up again as a gas. So we have our phases, solid, liquid, gas. We have a point at which both phases coexist, the boundaries, the plateaus, I should say. Those are going to be phase changes. So here we have melting, okay, and here we have boiling. That's kind of important that you see that, okay? And that's about it. The temperature is constant at the phase changes, increases, constant at the phase change, increases. Not a big deal. A prettier version is down here. Talk a little about kinetic energy. Kinetic energy increases as temperature increases. Potential energy increases the whole time you're heating. Okay, I have that written over here. Since it's a heating curve, potential energy is increasing the whole time. Kinetic energy relates to the motions of the particles. All right. At the plateaus, the particles aren't moving any faster. They're moving differently, but not faster. So the kinetic energy is staying constant. Potential energy is absorbing heat energy. Potential energy definitely increases the whole time. Cool. A cooling curve looks just the same, except different. Cooling curves, everything goes down. You have boiling, not. You have condensing. You have melting? No, you have freezing. Temperatures are the same. Just depends upon a point of view. Are you melting that ice or are you freezing the ice? It just depends upon the direction, but same idea. But since we're cooling, the potential energy decreases the whole time. And again, at the plateaus, kinetic energy is constant. Alrighty, so a little quicker video this time. It's just about the phases and the phase diagrams. And hope you have a good time. Hope you liked it. Have a great day.